Okay, hello everyone. So, how many have we got? 17. As usual, could I ask to turn your cameras on so I can have a look, so I can see if you understand what I'm doing? That'd be great. Let's give it one more minute. Okay, I think I'll make a start.
Recording in progress.
Right, hello everyone. So this is going to be our last tutorial on the communication side. So this is related to information theory. And then from tomorrow, we're going to be looking at signal processing. So I've uploaded the lecture notes for this week's signal processing lectures. So they're introductory. I think they're pretty simple. Starting off simple and getting a little bit more complicated with each week. So that's what we're going to do tomorrow. Today, we'll go through some questions on information theory, and they do take a long time, these questions, to answer because they're quite involved. So we'll try and do as many as possible. So hopefully you've got the tutorial sheet in front of you, so that I can switch to the whiteboard. So what I was planning to do was have a quick go through question 1 because that covers some fundamental knowledge, and then I thought I'll do question 2. Where are we? Sorry, I think I've got the wrong tutorial sheet. I'll change that in a minute. So there's on Canvas, you've got the more up-to-date tutorial sheet. I've uploaded the wrong one. So we'll do question 1. Okay, I'm just going to find the latest tutorial sheet. Second. Okay, so I can see that. Right, so question 1. We have got a discrete memoryless source with eight symbols, and so we need to know the probabilities of all the symbols. So let's write those down. Okay, so all those probabilities add up to 1, and what we have, first question, what is the information content in the following message? So basically, what is the information content of this message? BH F A E C, so just some random letters put together. And information content, of course, is the sum of the individual information. So it's a sum of the individual symbol information. So we've got basically this. So that's the information content of each symbol. And of course, the equation we're using is log to base 2 of 1 over the probability. So we've got log to base 2, 1 over 0.2. Plus log to base 2, oh, sorry, 0.04. Plus log to base 2 of h, which is, sorry, information of h, which is 0.1, so that's 1 over 0.1. Then for f, 0.03, so 1 over 0.03. A, log to base 2 of 1 over 0.2. And then E, 1 over 0.3. And then finally C, 1 over 0.07. Okay, and if we add all those together, we shall get the total information, which I'm just trying to find here. Here it is. So if we add all those together, what we get is 20.92 bits. So as always, if you have any questions about how I get the answers or any of the method, and please do use the chat. Okay. So part B, the source entropy. That is the average information of the source. So that's basically where we are generating an infinite number of random symbols between A and H, and calculate the average information per symbol. So if we take an extremely long sequence of random letters, add the information together, divide by the number of letters, then it will converge to an average value, which is the entropy. And it has a standard equation for any average value. So we add all the symbols together. Well, we multiply each symbol with its probability of it occurring. Multiplied by the information content, and add all those together. So as you can imagine, in this case, we've got 8 of these to add up, and so it would be this. So let's start from A. So probability of A times the information content in A. The probability of B times the information content in B. So those are that's the symbol, the probability of each symbol multiplied by the information content, all added together. And if you calculate that, you'll get 2.68 bits per symbol. Okay, so the source entropy is a very important quantity. Tells us the average information of the source before it's observed. And of course, later on, we have the conditional entropy, which gives us the information of the source after it's been observed. So very important that we understand how to calculate the source entropy. Now, the next question. Next question. If all 8 symbols are equally likely to occur, what is the source entropy? So at the moment, they're not equally likely. Every symbol's got its own probability. But if they're all equally likely, that means probability of A equals probability of B equals probability of C, etc. So we've got 8 symbols. So the probability of all the symbols are all equal to 1 over 8. Okay, so they're all equally likely, 8 of them, so it must be 1 over 8 for probability. So if we calculate the entropy in that case, then 8 symbols, and the probability is fixed at 1 over 8 for all symbols. So the information content of each symbol is also fixed, 1 over 8, log of 1 over 1 over 8. So that is equal to, so if we add that all together, we get So if we add all those together, what we get is log to the base 2 of 8. We actually calculate that sum, which is 3 bits per symbol. Much easier calculation because they all have the same information content and the same probability of occurring. So you can see that that is when the entropy is maximised, when each symbol is equally likely, we get the maximum entropy. So 3 bits per symbol is a maximum. So we can see that when the symbols aren't equally likely, then it falls short of the maximum 3 bits. So 2.68, slightly smaller than 3. Okay. So please do speak up or write if you do have any questions about any of the solutions. What I'd like to do next is actually skip question 2 because we've done that a few times already, and look at the erasure channel, question 3, because it did raise an interesting question, and the erasure channel does give slightly different values to what you expect. So 0 and 1 is our input. So probability of x equals 0 is 0.55. The probability x equals 1 is 0.45. And the probability of an erasure is 0.2. So that's the probability of the bit being erased. The probability of it being left alone is 0.8. So the first question is asking us to calculate the probability of y. And we have 3 probabilities. And to find these probabilities, we have to look at how different ways there are of achieving the symbol output. So for probability y equals 0, there's only one connection to 0, and that is obviously x equals 0. So y equals 0 is only connected to x equals 0. So you can see that here. There's no other connection. So that means that to get a 0, we have to start with a 0. So probability of 0, and the probability that it isn't erased. And that's it. There's no other possibility of getting y equals 0. So it will be 0.55 times 0.8, which is 0.44. Right, similarly for the bottom one, y equals 1, there's only one way you can get a 1. That's if you start with a 1. So probability y equals 1 is a probability that we start with a 1 and the probability that isn't flipped. Okay, so that's 0.45 times 0.8. Which is 0.36. And then finally, we've got the probability of an erasure. Of course, there are two possible ways of erasure. We can start with a 0 and it's erased, or we get a start with a 1 and it's erased. So probability x equals 0 and the probability that it's erased, or the probability we start with a 1 and the probability that it's erased. That's 0.55 times 0.2 plus 0.45 times 0.2. And that gives you the answer 0.2. So we add all those three numbers together, that should add up to 1. Okay. So the next question is determine the source entropy. So that's very simple. That's just a binary entropy function. So h of x so sum from I equals 1 to 2, because we've only got two input symbols, and that's probability of the symbol occurring times the information of that symbol. So simply that will be okay. So putting those values in, got 0.55 times log to base 2 1 over 0.55 plus 0.45 times log to base 2 1 over 0.45. You've all turned your cameras off again. Can't see if you understand or not, or if you can hear me. Okay. So if we put these numbers in, what we get is 0.9928. So that's the average uncertainty of the source, and it's very, very close to 1 bit per symbol because the probabilities are close to being equally likely. 0.55, 0.45, that's nearly 50-50, 55-45, so it's very close to being completely uncertain. So it's very close to the maximum, which would be 1 bit per symbol in this case. Now also, we can calculate the entropy of the source Y as well. Now, the reason why we're doing this is just to show the symmetry of mutual information. There's 2 different ways of getting mutual information. So we can actually calculate H of Y based on the 3 probabilities we calculated earlier. And so that would be 0.44 log to base 2, 1 over 0.44 plus 0.2 log to base 2, 1 over 0.2 plus 0.36 log to base 2, 1 over 0.36. And again, if we add those numbers together, we get an answer 1.5161 bits per symbol. Okay, so we don't expect it to be the same as H of X. 3 different probabilities. So we've got this. So the average uncertainty in Y is 1.5161. So what you can do, you can calculate the conditional entropy H of X given Y, which is the average entropy, which is the information in X after it's observed at Y. And you can actually do it the other way around as well. You can calculate the information in Y after it's been observed at X. So you can go backwards. So those are the 2 entropies we can calculate. Now the next part is to calculate the backward transition probabilities. Part C. So we've got calculate the probabilities, and we use Bayes' rule to calculate those. So we've calculated all these terms. Now remember, one that always catches people out, this term here, this is P, or 1 minus P. Okay, so if Y and X are the same, that's minus P. And if they're different, then it's P. So I'm aware that participants are starting to slowly drop off here. So it's gone down from 21 to 17. So when it gets to 0, I'll be worried. So if we want to calculate the probability X equals 0 given Y equals 0, then put in the values in. So we've got 0.55 times 0.8, because remember, this term here, that is 1 minus P, because X and Y are the same. 0.55 times 0.8 divided by the probability Y equals 0, which we calculated as being 0.44. And what you get is 1. So that was the surprising result that some of you got before. And the first reaction is, oh, it can't be right. It's 1. That's completely certain. It must be less than 1, surely. And it's not. That's actually the correct answer. And because if we go back to the diagram, so look at this blue line here. So this is y, this is x. So if I've received a y, then the only possible input must be x equals 0 with absolute certainty. So the probability of x equals 0 given y equals 0 is 1. Okay, so I've received y, it's 0. So therefore the probability of x being 0 is 1. So it is absolutely correct. And you'll get the same answer as well if you calculate the probability x equals 1 given y equals 1. For the same reason, there's only, if you've received y equals 1, then the only possible input can be x equals 1. So the probability is 1. So just to prove that, put the numbers in. And again, we get 1. So there's only 2 more left. So we've got probability x equals 0 given we've received an erasure. Now obviously that won't be 1 because there's 2 ways of getting an erasure. Putting the values in. Get 0.55. And again, it's another interesting result because this term here, this is P. And the probability y equals erasure given x equals 0 is the same as just the probability y equals e. Because it doesn't matter which bit you transmit, to get a bit erased, the probability is 0.2, regardless of whether you transmitted 0 or 1. So that's why the probability of y being an erasure is equal to 0.2, equal to p, because it doesn't matter what bit you transmit. If you get an erasure, it doesn't matter if it's 0 or 1, it's the same probability. Of course, it's going to be also same here. So again, the answer is the same as the probability x equals 1. So because as before, it doesn't matter because the probability of getting an erasure given you transmitted a bit is the same as just the probability of an erasure. So these terms cancel out. You're just left with probability of x. So the erasure channel does give more interesting results than the binary symmetric channel. Makes you think, the erasure channel. Okay. Okay, so now we've got to determine the conditional entropy. So this is the average information after we've observed it. So we're calculating h of x given y. We have all the probabilities we need. Let's go back to double summation. So we've got 2 input bits and 3 output symbols. And the equation we'll use is 1. The probability of y times the probability of x j given yi times log to the base 2 1 over the probability of x j given y I. So there's actually only 4 terms, although the summation suggests that the 6 terms, 2 of them are 0, because there's no connection between x equals 0 and y equals 1, and x equals 1 and y equals 0. So those 2 connections they never happen. There's probability 0, so we can ignore them. So it probably makes more sense if I actually just expand the summation, and so we get something like this. The last term, so that's every possible value of x and y, which are connected to each other. So there's 4 terms, and we have all of those probabilities calculated already. So just put the values in, and this is an interesting example because it actually simplifies quite a lot. So let's put the values in. So probability y equals 0 was 0.44, and the probability of x equals 0 given y equals 0 is 1, and then times the log to base 2 of 1 over 1. Now, log of 1 is 0, so that term disappears. Next term, probability of an erasure is 0.2 times probability x equals 0 given y equals e, which was 0.55, times log to base 2 1 over 0.55. And again, probability of an erasure times probability of x equals 1 given y equals e, which was 0.45, times log to base 2 1 over 0.45. And the last term, probability y equals 1, 0.45, times the probability y equals 1 given x equals 1, which is 1, times log to base 2 1 over 1. So again, log of 1 is 0. So those terms are going to disappear. So we only have to add up 2 numbers. And if we add those numbers together, what we get 0.1986 bits per symbol. Okay, so everyone clear with that? That's probably one of the two most difficult things you can do in information theory on this course is calculate the conditional entropy and calculate mutual information. So we did calculate mutual information last week. So we calculated conditional entropy this week. Now, just for completeness, we calculated the entropy of Y. We can also calculate the conditional entropy of Y given we transmitted X. So this is just the other way around. And as I said, this is just to demonstrate the symmetry of mutual information. So we can calculate h of y given x as a very similar equation. So the same summations. This time it's the probability of x I, so xj, sorry, times the probability of yi given xj times log to 1 over probability yi given xj. So again, we have all those probabilities. So remember that, of course, this is p, or 1 minus p. So we know that at the start. And we know x, probability of x. So again, if we just expand that, we get this. And the last term, so similar to the last one, just the x's and y's are reversed, aren't they? So okay, so now in this case, we're not going to get the simplification that we thought because we've got no probabilities equal to 1. It's a shame. But we put the numbers in. Let's do that very quickly. So put all the numbers in for those 4 terms. If we add them all together, we get the answer 0.7219 bits per symbol. Okay, so exactly the same method, just the probabilities are different, but the same method. So we've got these 4 values now. So taking those 4 values, we can calculate mutual information, the amount of information transmitted across the channel. There's 2 ways of getting that. So we can calculate h of x minus h of x given y, or h of y minus h of y given x. So if we put the values in, so h of x we calculated as being 0.9928, and then h of x given y was 0.1986, and that gives you an answer of 0.7942. Now, if we look at the other one, h of y, so we calculated that to be 1.5161. And then h of y given x, we just calculated to be 0.7219, and you subtract that away, and again you get the exact same answer, 0.7942 bits. There are 2 different ways of calculating the mutual information. So are there any questions at all? Okay, doesn't get any more complicated than that. Well, not in this module. You can go much deeper, of course, later on. But if you can understand that, then you're in very good shape for information theory. So, just want to explain the significance of the results, first of all. So, have we all written this down now? You see, I can't see your faces, so I don't know. I mean, you could all be playing on Xboxes for all I know. I can't see anything. Good, it's got some thumbs up. That's nice. So, so first of all, what I want to do, I just want to focus on x, the difference in the entropies. So you can see that at the start, the information of the source was quite high, well, very high, nearly the maximum value, 0.9928 bits, so nearly 1 bit. And then the information of the source after it's observed reduces significantly to 0.1986. And the reason is because the channel is quite is not harsh. The probability of a bit being erased is only small, it's 0.2. So basically 80% of the bits go through. So in that case, a lot of information is transferred across the channel. If P was higher, then less information will be transferred across the channel because it's a harsher channel. So mutual information is a measure of the quality of the channel. Now, very quickly, well, the last thing we can calculate is the capacity of this channel. And thankfully, that's a very, very easy thing to calculate because the capacity of an erasure channel is simply 1 minus P, where P is the probability of a bit being erased. So in that case, 1 minus 0.2, and that is 0.8 bits. So the capacity is 0.8 bits. That's the maximum rate we transmit information across the channel. That occurs when, so this is maximum mutual information. This occurs when the probability x equals 0 is the same as a probability x equals 1. Of course, it has to be 0.5. So if we were to change these probabilities to 0.5, then the mutual information we calculated would be 0.8. But you can see that we are very close to 0.8, 0.7942, and that is because the probability of x equals 0 is nearly the same as the probability x equals 1. So they're not the same, but 0.55 and 0.45 are quite close. So for that reason, the mutual information is close to the capacity. Okay, so that's the significance of the numbers we've calculated. Okay, are there any questions that you'd like to ask? Okay, so if everyone's happy, then I don't really have enough time to go through any other questions. What I will say is, if I look at tutorial 5, yeah. So question 5 is obviously a Huffman coding question. I think that you should be able to answer that based on the lecture notes, but I will be handing out the solutions to these tutorials very soon anyway. So I think probably a good place to leave it there, because we have covered a lot, and it's a lot of writing in this tutorial. So thank you all very much. If there's no more questions, I will let you go and see you tomorrow. Okay, thank you very much. Goodbye.